Now we are going to discuss adjoint and inverse of a matrix. Now first definition is adjoint of a square matrix A. So adjoint of A is defined as replace each entry by its cofactor and take the transpose. That is, the entry at the place A11 will be replaced by its cofactor capital A11. The entry at the place A12 will be replaced by capital A12, that is cofactor of A12, and so on. Replace each entry by its cofactor and then take the transpose. You will get adjoint of A. Now the next definition is inverse. A square matrix A is said to be invertible if there exists a square matrix B of the same order as A. If there exists a square matrix B whose order is same as that of A, and this matrix B satisfies the property that A into B is equal to I is equal to B into A. In such cases, B is known as inverse of A, and we write B is equal to A inverse. And therefore 1 can be written as, and therefore 1 implies A into A inverse is equal to I is equal to A inverse into A. Write A inverse instead of B here. So we get this. A matrix A is said to be singular if determinant of A is equal to 0, and non-singular if determinant of A is not equal to 0. I take up a very important property of adjoint of a matrix. Now A into adjoint of A is equal to determinant of A into I is equal to adjoint of A into A. If we divide this equation by determinant of A, we will get A into adjoint of A over determinant of A. And here determinant of A will cancel, we will get I, and here adjoint of A over determinant of A into A. So what we notice, A into B is equal to I is equal to B into A. That is, this property is satisfies. That is, so what we notice, A into B is equal to I is equal to B into A. That is, this property is satisfies. That is, A inverse must be equal to adjoint of A over determinant of A. Here, since we are dividing by determinant of A, therefore determinant of A must not be equal to 0, because division by 0 is not possible. So A inverse is adjoint of A over determinant of A, and this is a very useful definition for solving numericals. I discuss two more properties. Sixth is adjoint of AB is equal to adjoint of B into adjoint of A. And this property is known as the reversal law. Adjoint of A into B is not equal to adjoint of A into adjoint of A. It is equal to adjoint of B into adjoint of A. And we know in matrix multiplication is not commutative. Therefore, adjoint of B into adjoint of A is not equal to adjoint of A into adjoint of B. So, adjoint of AB is adjoint of B into adjoint of A. That is, the order of B and A is reversed. This is known as reversal law. And this reversal law is again true for matrix inverse. AB inverse is not equal to A inverse into B inverse. It is equal to B inverse into A inverse. This is also known as the reversal law. This is also known as reversal law. We have discussed adjoint and inverse of a matrix. I am going to take some questions based on these two topics. First question is, find the inverse of the matrix A is equal to this much and verify that A inverse into A is I3, identity matrix of order 3. So we are given A is equal to this much. Now we define A inverse is equal to adjoint of A over determinant of A. A inverse is adjoint of A over determinant of A. And adjoint of A is defined as replace each entry by its cofactor and take the transpose. So first step will be, we have to find the cofactors of each and every entry of this matrix. So what we do is, we find the cofactors of the first row first. Cofactors of first row R1 are. Now we find the cofactor of the entry at the first place, that is this entry. So this column and this row will be gone, and we will be left with 4, 1, 7, 2, and this place is 1, 1. So this will be positive. So first will be positive, and we will get this is gone, this is gone. 4, 1, 7, 2. 4, 1, 7, 2. This is the first cofactor. And second cofactor, this is odd place. 1, 2. 1 plus 2 is 3, odd. So this will be negative, and we will delete this column and this row. Delete the row and column in which the entry occurs. This is the entry. Delete this and this. We are left with 3, 1, 3, 2. Now next entry is this. Now place of this entry is 1, 3. First row and third column. That is, this is an even place entry. So this will be plus, and this will be deleted, this will be deleted, and we will be left with 3, 4, 3, 7. 3, 4, 3, 7. Now you evaluate, this is 8, 8 minus 7 is 1. And this is 6 minus 3. 6 minus 3 is 3, and there is a negative sign. This will be minus 3. This will be 7 3s are 21. 21 minus 12. That is 9. Now we find cofactors of second row. Cofactors of second row. That is this. Now this is entry at the place second row first column. That is odd. So this will be negative. And we will have, this will be deleted, this will be deleted. We will get 3, 1, 7, 2. 3, 1, 7, 2. Now next is even, so we will have plus sign. This row and this column will be deleted. We will be left with 2, 1, 3, 2. 2, 1, 3, 2. Now next entry will be negative. Odd, even, odd. So they will be alternate plus minus signs. So this will be, now this is deleted, this is deleted. We are left with 2, 3, 3, 7. 2, 3, 3, 7. And on evaluation, this gives 6 minus 7. Minus 1, minus, minus, plus. So this will be plus 1. This is 4 minus 3. 4 minus 3 is 1. And this is equal to 14. 14 minus 9. That is 5. So minus 5. And cofactors of R3 are, now we find the cofactors of R3. So R3, this. So place of this entry is third row and first column. 3 plus 1 is 4, even. So this will be plus, and this is gone, this is gone. 3, 1, 4, 1. 3, 1, 4, 1. And next will be negative, and this will be, now this is the place of the entry, the row and column in which the entry occurs. This entry occurs in this row and this column. So 2, 1, 3, 1. 2, 1, 3, 1. And next is this place. So this column and this row will be gone. We will be left with 2, 3, 3, 4. 2, 3, 3, 4, and there will be alternate plus minus sign. Plus, minus, plus. So on evaluation, this gives 3 minus 4. That is minus 1. And this will be equal to 2 minus 3. 2 minus 3 is minus 1, minus minus plus 1. And this will be equal to 8. 8 minus 9 is minus 1. So this is equal to minus 1. Minus 1. Now determinant of A. Determinant of A is equal to, now what we do, these are the cofactors of first row. So determinant is nothing but sum of products of the entries of a row with the corresponding cofactor. So 2 into 1, 3 into minus 3, and 1 into 9. 2 into its cofactor plus 3 into its cofactor plus 1 into its cofactor. So determinant will be 2 into 1 plus 3 into minus 3 and 1 into 9. So this will be 1 into 9. And this is equal to, now 9 minus 9 is 0, and this is 2. So value of the determinant is 2. Now in order to find adjoint of A, what we have to do is we have to replace each entry by its cofactor. So we will get a matrix in which entries are 1, minus 3, 9, 1, 1, minus 5, minus 1, 1, and minus 1. So we write this matrix as adjoint of A is equal to, now in first row write the cofactors of the first row, which are 1, minus 3, 9, and cofactors of second row are 1, 1, and minus 5, and cofactors of third row are minus 1, 1, and minus 1. You can see the side sheet. So adjoint of A is this transpose, that is equal to, now transpose is interchange rows and columns. So this row will become first column, 1 minus 3, 9. This row will become second column, 1, 1 minus 5. Interchange the rows and columns. So this will be minus 1, 1 minus 1. This is adjoint of A. And now A inverse is equal to adjoint of A divided by determinant of A. That is equal to 1 by 2 of 1, 1 minus 1 minus 3, 1, 1, 9 minus 5 minus 1. And the rule for scalar division in matrices is divide each and every entry by this scalar. So we will divide each and every entry of this matrix by 2, and we will get 1 by 2, 1 by 2 minus 1 by 2. This is minus 3 by 2, 1 by 2, 1 by 2. And this will be 9 by 2 minus 5 by 2 and minus 1 by 2. So this is the required inverse. Now the second part is verification, that is A inverse A is equal to I3. Now we have to find this matrix multiplication and show that this comes out to be I3. So A inverse A is equal to, I will take inverse in this form, because this will introduce a lot of fractions and this will complicate the calculation. So what we write is 1 by 2 into 1, 1 minus 1 minus 3, 1, 1, 9 minus 5 minus 1. Take A inverse in this form. This will avoid the fractions. So this into A, and A is 2, 3, 1, 3, 4, 1, 3, 7, 2. So this will be equal to 1 by 2 into. Now matrix multiplication is a row column multiplication. First row will get multiplied by this column, then this row will get multiplied by this column, and this row will get multiplied by the third column. So what we get is 2 plus 3 minus 3. 2 plus 3 minus 3. Now we multiply this row with this column. What we get is 3 plus 4 minus 7. 3 plus 4 minus 7. And now we multiply this with the third column. So what we get is 1 into 1 is 1 plus 1 into 1 is 1. 1 plus 1 minus 2. 1 plus 1 minus 2. Now we repeat the process with the second row. Second row into this, into this, into this. So second row multiplied by this. Minus 6 plus 3 plus 3. Minus 6 plus 3 plus 3. Now this multiplied by this. So this will be minus 9 plus 4 plus 7. Minus 9 plus 4 plus 7. So next will be this into this. So this will be minus 3 plus 1 plus 2. Minus 3 plus 1 plus 2. Now we multiply third row with first column, second column and third column. So first column, 18 minus 15 minus 3. 18 minus 15 minus 3. And this into this will be 27 minus 20 minus 7. 27 minus 20 minus 7. Now this into this. This will be 9 minus 5 minus 2. 9 minus 5 minus 2. and this on simplification gives us 1 by 2 into, this will be 3 and 3 cancels, we are left with 2. Now this is 7 minus 7 is 0. This is 2 minus 2 is 0. 6 minus 6 is 0. 11 minus 9 is 2. 3 minus 3 is 0. 18 minus 18 is 0. 27 minus 27 is 0. This is 9 minus 7, that is 2. So what we get is, now divide each and every entry by 2. This is the rule for scalar multiplication in matrices. So this will be 1, 0, 0, 0, 1, 0, 0, 0, 1. That is equal to I 3, hence verified. Now there are few questions for you to try. Find the adjoint of the matrix this and verify that A into adjoint of A is equal to determinant of A into I3 into adjoint of A into. And we know adjoint of A is replace each entry by its cofactor and take the transpose. So what you do is find the cofactors of first row, second row, third row, and then substitute it adjoint of A and take the transpose. So then complete this matrix multiplication and verify this. And second question is, for the following pair of matrices, verify that AB inverse is this much. What we do is, in this case, we first find AB. Now what we do is, we multiply these two matrices using matrix multiplication, and we will get AB and then find its inverse. First find AB and then its inverse, and then find inverse of B, inverse of A, and multiply B inverse, A inverse, and verify that these two sides are equal. That is, reversal law is true. And third is, if A is equal to this, show that A inverse is equal to A square. Now direct method will be find A inverse and find A square and see whether they are equal or not. Or a shorter method will be, we have to prove that A inverse is equal to A square. That is, multiply by A both sides. So we will get A into A inverse is equal to A into A square. Pre-multiply this equation by A. So A into A inverse is I, and this is equal to A cube. So what we do is, we will prove, find A cube and prove that this is equal to I. Multiply A with A to get A square, and then multiply A square with A to get A cube, and it will come out to be I. Now after proving this, multiply both sides by A inverse, or we can say pre-multiply both sides with A inverse. So A inverse into A cube is equal to A inverse into I, and this can be written as A inverse, and A cube can be written as A into A square. Now using associative law, we can take this in one bracket, and this will be equal to A inverse into I will be A inverse, and this will imply that this is identity. So this will be I into A square is equal to A inverse, and this will imply A square is equal to A inverse. This method will be shorter. You prove A cube is equal to I and then pre-multiply it with A inverse. You will get A square equal to A inverse. Pre-multiply this with A inverse. A inverse into A cube will be A inverse into I. Now we can write A cube as A into A square and associate these two. What we get is this will be identity A square A inverse, and I into A square is A square. So this is equal to this. You can try these three questions yourself. Now I take up this question. Let this matrix be denoted by A, this by B, and this by C. Then this equation can be written as this is A x B. A x B is equal to C. Now this equation can be written as A x B equal to C. Now we have to find x. So what we do is we multiply this equation from the left by A inverse and right by B inverse, so that A inverse into A will become identity and B into B inverse will become identity, and we will get x. First we multiply this equation from left by A inverse. We get A inverse into AX B is equal to A inverse C. So what we get is by associativity, this is equal to A inverse A into, these brackets can be changed, XB is equal to A inverse C. So this is I into XB is equal to A inverse C, and I into this is this matrix itself. So this will be XB is equal to A inverse C. Now in order to remove B from here, we multiply, see this equation has 2, multiply 2 from right by B inverse. So what we get is XB into B inverse is equal to A inverse CB inverse. Or by using associativity, we can write this as X into B inverse is equal to A inverse CB inverse. Now B into B inverse is identity. So X into I is equal to A inverse CB inverse. And X into I is X. So we get X equal to A inverse CB inverse. Now in order to find X, we will find A inverse CB inverse. So first is determinant of A. Determinant of A is 15 minus 14, that is 1. Determinant of B is equal to minus 1 plus 2, that is 1. And determinant of C is 8 minus 0, that is 8. So A and B are invertible. To find A inverse. A inverse is equal to adjoint of A over determinant of A. Now in order to find adjoint of A, what we do is replace each entry by its cofactor. Replace each entry by its cofactor and take the transpose. Replace each entry by its cofactor and then take the transpose. Cofactors of R1 are, now cofactor of this entry. This is deleted, and we are left with 5. And this is 1, 1. So 1 plus 1 is 2. Even place, we will have plus. So this will be plus, and this is gone, we will have 5. and this place is odd place, so we will have negative sign, and this will be gone, this will be gone. Delete the row and column in which the entry occurs. These will be deleted and we will be left with 7. So cofactors of R2 are, now this place is second row first column, 2 plus 1 is 3, odd place, so negative, so this will be minus, and this is gone, 2. Next place is even, 2 2, so this is gone, we are left with 3. So adjoint of A will be equal to, now replace each entry by its cofactor. Replace entry at this place with its cofactor. This -2 3, and take the transpose. So this is equal to 5 minus 7 and -2 3. Interchange the rows and column. This row will become first column, second row will become second column. So adjoint of A is equal to this, and therefore A inverse is equal to adjoint of A over determinant of A. But determinant of A is 1, so this is equal to adjoint of A. So this is equal to 5 minus 2 minus 7 3. So A inverse is this much. And similarly you can find B inverse by doing the same steps as we did for A inverse. I am directly writing B inverse. B inverse is equal to 1 minus 1 2 minus 1. B inverse is 1 minus 1 2 minus 1. Now in order to find x, x is equal to A inverse CB. A inverse CB inverse. X is A inverse CB inverse. Now we substitute A inverse CB inverse here. We get A inverse is this much, C is this much, and B inverse is this much. Now we carry out this multiplication. We can associate these two, that is we will first multiply these two and then multiply the result with this, or you can associate these two. You can do it any way. So this is equal to, now this into this. Now matrix multiplication is row column multiplication. This row will be multiplied with this column, this row will get multiplied with this column. So this row with this column, we will get 5 into 2 is 10, minus 2 into 0 is 0. So we get 10. Now this into this, minus 5 minus 8 minus 13. This into this is minus 14 plus 0. This is minus 14 plus 0. This into this, minus minus plus 7 plus 12. This is 19. So we get this. Now again, in order to multiply these two matrices, this into this. So this will be 10 minus 26. 10, this into this, this into this. So 10 minus 26 is minus 16. This into this, minus 10 plus 13. Minus 10 plus 13 is 3. This into this, minus 14 plus 38. This is equal to 24. Now this into this is plus 14 minus 19. Plus 14 minus 19 is minus 5. So this is the answer. Now this question you can try yourself. What you do is let this be A and this be B. So this equation will become XA is equal to B. Now multiply to the right by A inverse. We will get XA into A inverse will be equal to B into A inverse. Now this is equal to X into A inverse is equal to B A inverse, and this is identity. So X into I is equal to B A inverse, and X into I is X. So we get X equal to B A inverse. You can try it yourself. We will move on to the next question. Next question is, for the matrix this show that A square minus 4A plus 5A I is equal to 0. Hence obtain A inverse. Now first is A is given to be 1, minus 1, 2, 3. What we do is we find A square. A square is A into A. This is equal to 1 minus 1, 2, 3 into 1 minus 1, 2, 3. Now matrix multiplication is row column multiplication. So this into this is 1 minus 2. So 1 minus 2 is minus 1. This into this. This is minus 1 and this is minus 3. Minus 1 minus 3 is minus 4. So this into this. So 2 plus 6 is 8. This into this. Minus 2 plus 9. Minus 2 plus 9 is 7. So we get A square is equal to this much. And therefore A square minus 4A plus 5I is equal to, how much is A square? A square is minus 1, minus 4, 8, 7. Into minus 4 into A. A is 1, minus 1, 2, 3. And 5I. I is 1, 0, 0, 1. So what we get is minus 1, minus 4, 8, 7. And multiply each and every entry by minus 4. We prefer plus sign here. So we multiply by minus 4. Each and every entry by minus 4. So this will be minus 4. This will be 4. This will be minus 8 and minus 12. Plus 5i. Multiply each and every entry by 5. We get 5, 0, 0, 5. Now addition is add the corresponding entries. What we get is minus 1, minus 4 plus 5. That is minus 5 plus 5 is 0. Minus 4 plus 4 is 0. 0 plus 0 is 0. Now and add the entries at this place. Plus 8, minus 8, 0. So 8 minus 8 is 0, plus 0 is 0. And 7 minus 12 is minus 5, plus 5 is 0. So we have proved that A square, hence A square minus 4A plus 5I is equal to 0. Now next is obtain A inverse. To find A inverse, what we do is we multiply equation 1 by A inverse from right. So this will be A square into A inverse minus 4 A inverse plus 5I into A inverse is equal to 0 matrix. Now this can be written as A into A. A square can be written as A into A. And by using associative law, we can associate these two. And we get 4I plus I into A inverse is 5A inverse. This must be equal to 0. And therefore, A into I, this is I, minus 4I plus 5A inverse is equal to 0. And therefore, A inverse is equal to, A inverse will be, we will take these to the other side. So what we get is 4I minus A. 4I minus A divided by 5. 5A inverse is equal to 4I minus A. A into I is A. So A inverse is 1 by 5, 4I minus A. And this is equal to 1 by 5 into 4I. 4I will be equal to 4004 minus A. How much is A? A is 1 minus 1, 2, 3. So this is equal to 1 by 5 of 4 minus 1. 4 minus 1 is 3. 0 minus 1 is plus 1. And this is equal to 0 minus 2 is minus 2. And 4 minus 3 is 1. So we get this equal to, now what we do is multiply each and every entry by 1 by 5. So we get 3 by 5. This will be 1 by 5. And this will be minus 2 by 5. This will be 1 by 5. So this is the required value of the inverse. 3 by 5, 1 by 5, minus 2 by 5 and 1 by 5. You can directly verify it by calculating the inverse. Now this question, this is similar to this. If A is equal to this, verify that this is equal to 0 and hence find A inverse. First what we do is we find A square. We multiply A with A and get A square. Then multiply A square with A to get A cube. Substitute in the left hand side of this equation and verify that it comes out to be 0. And then to find A inverse, what we do is we will multiply this equation by A inverse. So when we multiply this equation by A inverse, we will get A inverse into this will be A square minus 6A plus 9I minus 4A inverse. And solve this equation for A inverse. And calculate it as we have done here. You can try it. Now, this is the last question I am going to take up. So, what we do is we have to prove that A transpose into A inverse is this much. A transpose into A inverse is this much. So A transpose is equal to interchange the rows and columns. First row will become first column, 1 tan x, and this is minus tan x into 1. Second row will become second column. To find A inverse. A inverse, we first find determinant of A. Determinant of A is this into this is 1 and minus this into this, minus minus plus tan square x, and this is equal to secant square x. This is secant square x. And now cofactors of R1 R. In order to find adjoint of A, what we do is we will find the cofactors of each and every entry and replace those entries by their cofactors. So cofactors of R1, cofactor of this is even place, 1 1. This is gone, this is gone, and we get 1. First cofactor is 1, then this will be negative. So this is gone, and we get minus minus plus tangent x. Cofactors of R2 are cofactor of this is second row first column. 2 plus 1 is odd, odd is negative, so this is gone, we get minus tangent x. Next entry is 2 2 even, so this is gone, we get plus 1. Therefore adjoint of A is equal to, replace each entry by its cofactor. So we get 1 tangent x minus tangent x. These are the cofactors of various entries. This transpose, and this is equal to now transpose of this. This row will become first column. Second row will become second column. So we get this. Adjoint of A is this much, and A inverse is equal to adjoint of A over determinant of A, and this is equal to, how much is determinant? Determinant is 1 by secant square. So 1 by secant square x into 1 minus tangent x 1, and this is equal to, now multiply each and every entry by 1 by secant square x. So 1 by secant square is cos square x. So this will be cos square x, and this will be minus tangent x into cos square x, and this will be equal to tangent x into cos square x, and this will be cos square x. So this is equal to, now tangent x into cos square. Tangent x is sin x over cos x into cos square x. So what we get is these two cancel, and we get sin x into cos x. So this is equal to cos square x into minus sin x cos x, and this will be sin x cos x as explained here. So this will be cos square x. Now we have to find A dash into A inverse. Therefore A dash into A inverse is equal to, how much is A dash? A dash is 1 minus tangent x into 1 into A inverse. A inverse is cos square x sin x cos x into sin x cos x into cos square x. This is equal to this into this. We get cos square x minus tangent x into sin x cos x. This is the first entry. This into this minus sin x cos x minus tangent x into cos square x. Now this into this will be equal to tangent x into cos square x. Tangent x into cos square x plus sin x cos x. Now this into this will be minus tangent x into sin x cos x. Tangent x into minus sin x cos x plus cos square x. This will be cos square x. And this is equal to this is sin x by cos x. So what we get? Sin x by cos x. Cos x cancels, we get sin square x. So what we get here is cos square x minus sin square x. This will be minus sin x cos x. This will be sin x over cos x. Cos cancels, we get minus sin x cos x. So what we get is minus 2 sin x cos x. And this will be again sin x over cos cancels, sin x cos x. Sin x cos x. So 2 sin x cos x. And this will be equal to, now sin and cos cancels, we get minus sin square x cos square x. This is minus sin square x plus cos square x. So this is equal to cos square x minus sin square x is cos of 2x. Minus 2 sin x cos x is minus sin 2x. And this is again sin of 2x. And this is cos square x minus sin square x, cos 2x. These are the basic formulae from trigonometry. Cos square x minus sin square x is cos 2x, 2 sin x cos x is sin 2x. And we get the result. Before ending up this topic, I will like to make a very small point. Suppose we are given A is equal to A, B, C, D. And we have to find its adjoint. So adjoint will be, we first will find cofactors of R1, R. This is even place entry, so plus. This is gone, this is gone. We will have plus D. Cofactor of this is gone, this is gone. C, and place of this entry is first row, second column, odd. So minus C. And cofactors of R to R. Now this is odd place entry. Second row, first column. 2 plus 1 is odd, so we will have a negative sign. This is gone, we will have minus B. And this is even place entry, this is gone, we will have a plus A. Therefore, adjoint of A is equal to. Place each entry by its cofactor. So first is D. D minus C minus B A. And take the transpose. Replace each entry by its cofactor and take the transpose. So what we get is, take the transpose. This row will become first column, D minus C. This will be the second column, minus B. So what we see here, that in order to find adjoint of a 2 cross 2 matrix, what we do is we interchange these two entries. These two entries have been interchanged, DA, and attach a negative sign with these. Interchange these two entries and attach a negative. So this will be DA. D will come here, DA minus C minus B. This is DA minus C minus B. So if you can remember it, just memorize that adjoint of a 2 cross 2 matrix is interchange the diagonal entries and attach negative signs. So what we do is interchange diagonal entries. So D comes here and A comes here, and attach negative signs with the other two entries. So we will get DA and minus C minus B. For example, A is equal to this much, and we have to find adjoint of A. So adjoint of A will be equal to, what are the keywords? Interchange diagonal entries. Interchange these two diagonal. 3, 1. We have interchanged the diagonal entries and attach a negative sign with others. Now with other two entries, we have to attach a negative sign. 2 will become minus 2 and minus 1 will become 1. So this will be the adjoint. This will be the adjoint. And if you have to find inverse, just divide it by determinant of it. That is 3 plus 2, 5. Divided by 5, you will get inverse. So keywords are interchange diagonal entries, and attach negative signs here. So if you can remember it, just remember it. It will save time in competitive exams. We will discuss two very fundamental operations involved in mathematics and their properties. First operation is addition and second is multiplication. First I will discuss it for real numbers and then for matrices. Now first property is commutativity. Now commutativity of addition. If A and B are two real numbers, then A plus B is equal to B plus A. That is, their order can be changed. A plus B is same as B plus A. 2 plus 3 is same as 3 plus 2. This is the first property, commutativity. And commutativity in multiplication will be A into B is equal to B into A. That is, their order can be interchanged. And second operation is associativity. Associativity means if we have A plus B plus C is equal to A plus B plus C, we associate these two or we associate these two, the result is same. That is, if I first add A and B and then add the result to C, the result will be same as when we add B and C first and then add the result to A. This property is known as associativity. Associativity means that these brackets, place of these brackets can be changed. And commutativity means order of these two can be changed. A plus B is same as B plus A. And associativity in multiplication will mean A into B into C is equal to A into B into C. If I associate these two or I associate these two, the result will be same. That is, if we multiply A and B first and then multiply the result with C, it will be same as multiplying B and C first and then multiplying the result with A. The result will be same. This property is associativity. And third is existence of identity. There exists a real number 0 belonging to R such that A plus 0. That is, there exists such a number 0 which when added to A leaves it unchanged. Then such a number is known as identity. A plus 0 is equal to A is equal to 0 plus A. If we add 0 to A from right or from left, the result is A. Identity is that number which when added to this leaves it unchanged. And identity for multiplication will be what is that number which when multiplied with A will leave it as A. This can be done from left or from right. What is that number which when multiplied with A leaves it unchanged? That is 1. A into 1 is A, or 1 into A is A. This number is known as identity. There exists one belonging to R such that this is this. So additive identity is 0 and multiplicative identity is 1, because when 0 when added to A leaves it unchanged. So this is the additive identity. And multiplicative identity is 1, because if I multiply A with 1, any number with 1, it remains unchanged. Fourth property is existence of inverse. For every A belonging to R, there exists minus A belonging to R such that. Now what is inverse? Inverse is that number which when added to A gives us identity. Additive identity is 0. So what is that number which when added to A gives us identity from right as well as from left? So what is that number? A which when added gives us identity. So what should be added to A? Minus A. If we add minus a to a, we will get identity, that is 0. So minus a is the additive inverse. And similarly, multiplicative inverse. Multiplicative inverse is that number which when multiplied with a gives us identity. Which identity? Multiplicative identity. Operation is multiplication. So multiplicative identity is 1, and this is equal to this into a, which when multiplied with a from right as well as from left gives us identity. So what is that number? That number is 1 by a, and 1 by a is written as a to the power of minus 1. A to the power of minus a inverse. For every a not equal to 0 belonging to R, there exists a inverse belonging to R such that this is true. But this exists only for non-zero numbers. Inverse of 0 does not exist. 1 by 0 is not possible. So these are the 4 fundamental properties of addition and these 4 for multiplication. All the processes involved are done by using these properties. Subtraction is including in addition. A minus B. Then it will be A plus inverse of B is minus B. Now we discuss the above properties for matrices. I have discussed all these properties while discussing matrices. I am very briefly once again discussing these properties. Now first I discuss commutativity for addition. Then I will discuss commutativity for matrix multiplication. So first is commutativity for addition. If A and B are any two compatible matrices, then we say that A plus B is equal to B plus A. A plus B is equal to B plus A. That is commutativity of addition is true in matrices. And A into B, A, B, C, all the matrices involved here are compatible for addition and multiplication. So A dot B is not equal to B into A. This is the first situation which we study in which commutativity is not true. That is 1 into 2 is not 2 into 1. A into B is not equal to B into A. In matrices, A into B is not equal to B into A. Now A plus B is equal to B plus A. So commutativity is not true in matrices. And second property is associativity. A plus B plus C is equal to A plus B plus C. If we associate these two or we associate these two, the result is same. Associativity is true for matrix addition, and similarly associativity is also true for matrix multiplication. A into B into C. If we associate these two or we associate these two, the result will be same. And third property is existence of identity. Let A be any M cross N matrix, then there exists a matrix of the same order as A. that is m cross n, such that 0 when added to A leaves it unchanged. If it is added from right or to left, the result remains unchanged. That is, A remains A. A plus 0 is A is equal to 0 plus A. And for multiplication, let A be any square matrix of order n, then there exists a matrix of the same order as A, that is In, such that A into In leaves A unchanged. That is, we get A, and In into A is same as A. Then such a matrix is the identity, as in numbers. A into 1 is A is equal to 1 into A, then we say that 1 is the identity. But here identity exists only for a square matrix. Only for square matrices. It does not exist in general. If A is m cross n, then identity does not exist. And fourth property is existence of inverse. Now if operation is addition, then for every A of order m cross n, there exists a matrix minus A of order m cross n, such that A plus minus A is equal to identity of order m cross n is equal to minus A plus A. A plus minus A is identity, and minus A plus A is also identity. Now for matrix multiplication, for every square matrix A non-singular, there exists a matrix A inverse such that A into A inverse is equal to I, is equal to A inverse A. Now here also the inverse exists only for non-singular square matrix. Non-singular means determinant of A is not equal to 0. So for every non-singular square matrix A, there exists a matrix A inverse such that A into A inverse is equal to I is equal to A inverse into A. Now these are the fundamental properties of addition in real numbers, multiplication in real numbers. Addition in matrices, multiplication in matrices. This is commutativity for addition, commutativity for multiplication is not true. Associative for addition is true, associativity for multiplication is also true. Existence of identity. Now in addition, there exists identity for all the matrices. But in multiplication, identity exists only for square matrices. In addition, for every A m cross n, there exists minus A. That is, inverse of every matrix exists. But in multiplication, inverse exists only for non-singular matrices. So here identity exists for all the matrices. Here identity exists only for square matrices. Here inverse exists for all the matrices. Here inverse exists only for non-singular matrices. And the properties A plus 0 is A is equal to 0 plus A. A into In is A is equal to In into A. And here A plus minus A is 0. Here A into A inverse is multiplicative identity. This is the additive inverse and this is the multiplicative inverse. If operation is addition, then what is that matrix which when added to A gives us the additive identity? And if operation is multiplication. What is that matrix which when multiplied with A gives us multiplicative identity? So these are the fundamental properties. And now I consider a very simple equation. Say A x b is equal to c. This is in real numbers. A, B, C, X are all real numbers. Now in order to solve this equation, what we do is we write X into B is equal to C by A is equal to A inverse C. Now what we are doing is we are taking A to the right hand side. But this is not a mathematical operation. Take A to the right hand side. What is the mathematical operation involved? Mathematical operation involved is divide both sides of 1 by A. And this is equivalent to multiply both sides of 1 by A. This is same as multiplying divide by A means same as multiply both sides by 1 by A. And this is same as multiplying both sides of 1 by A inverse. So what we do is multiply both sides of 1 by A inverse. A inverse AXB is equal to A inverse C. Because associative law is true for multiplication in real numbers. So we can associate these two and these two and we get A inverse C. We can change the position of the bracket. That is A inverse into A is 1. 1 into XB is equal to A inverse C. Now what we do is we associate these two. Now 1 into X is X. We are trying to understand the very minute operations involved in solving this equation. The first operation is multiply both sides by the inverse of A. And then we are using associative law and we know by property of existence of inverse, A inverse into A is 1. And then again 1 into X is X. This is existence of identity. So these are the various properties involved in reaching here. So we directly say that AX into B is C, therefore XB is equal to this much. But these are the various properties used in reaching from this equation to this equation. Now what we do here is multiply both sides by B inverse. What we get is XB into B inverse is equal to A inverse C into B inverse. Using associative law, we can write this as B into B inverse. This is equal to A inverse C B inverse. And this is X into 1 is equal to A inverse C B inverse. That is X B into B inverse is 1. And X into 1 is X. Because this is the identity. So we get A inverse C B inverse. So these are the various mathematical operations or properties involved in getting this equation solved for x. We generally directly do. AXB is equal to C, therefore x is equal to C over AB. That is A inverse C, B minus 1. But these are the various properties used. And since in matrices some of these properties are true and some are not, so we must understand, we cannot directly write x is equal to this much. We must understand which property is being used. So this was the purpose of telling this. We must understand what properties are being used. Now I translate this for matrices. Now I take up a very simple matrix equation parallel to this, where A, X, B are all square matrices compatible for matrix multiplication. Now in order to solve this, now there is no such process by which we can say that x into b is equal to c divided by. C divided by A means nothing in matrices. So what we do is we multiply to the left by A inverse. Multiply to the left by A inverse. Now we must specify from which side we are multiplying. For example, we have A. If I multiply it from left, we will get BA. And if I multiply A from right by B, we will get AB. And AB is not equal to BA. So from which side we are multiplying is important in matrices. So what we get is A inverse into AXB is equal to A inverse C. Now using associativity, A inverse A into XB is equal to A inverse C. These brackets can be changed. So A inverse A is I. So we get A into A inverse is I, and we get IXB is equal to A inverse C. So I into XB is XB. So we get this equal to this. Now in order to remove B, what we do is multiply to the right by B inverse, and what we get is XB into B inverse is equal to A inverse C into B inverse. And by using associativity, we can write this as X into B inverse is equal to A inverse C B inverse. Using associativity, I can change the position of these brackets. So what we get is B into B inverse is identity. This is equal to A inverse C B inverse, and Xi into X. Now Xi is equal to X, and we get A inverse CB inverse. Now in real numbers, I illustrated you how to solve this equation and understand the various minute processes involved. And in matrices, we carry out these minute processes, then we solve this equation in this way. AXB is equal to C, multiply by A inverse to the left, we will get A inverse into A. This will become identity. I into X will be X. So we'll be left with X into B. And in order to remove this B, what we do is we multiply from the right by B inverse. So B into B inverse will be I, and we will get X. So first is multiply to the left by A inverse. This is I, and we get this. Now we have to remove this in order to get X. So multiply to the right by B inverse. What we get is XB into B inverse is this much. Now associativity gives this. This is I, and we get